This is a video to help you through the activity on stereoisomers and chiral centers. Before we start, I want to point out that single bonds are freely rotatable. If I have a molecule like this, which is made of all single bonds, I can arrange this molecule so that both of these green groups are on the same side, but I can also rotate freely around the single bond so that the green groups are opposite of each other. This is why it doesn't matter how we draw our skeletal structures for simple molecules that have single bonds. For example, butane. All of these are representations of butane. They're all correct skeletal structures, and it doesn't matter the orientation in which we draw the two methyl groups on the end of the two center carbons, because I can freely rotate around single bonds. So any of those representations can represent a molecule that has 4 carbons and all single bonds. This is not the case when we have rings or double bonds, because you cannot freely rotate around rings and double bonds. Here is an example of a molecule with a ring that has 2 groups on the same side of the ring. This is similar to the cis 1,3-dimethyl-cyclopentane on the slide in front of you. I can't freely rotate these bonds anymore. They're stuck. And so these 2 groups are stuck in the cis position, or on the same side of the ring. And therefore, a molecule that has a different orientation of those groups, in the trans orientation, basically where one group is stuck on the opposite side of the ring than the other, is different. And now these are 2 different isomers. One is the cis isomer and one is the trans isomer. Cis means same side and trans means across from. This is also the case with double bonds. You can't freely rotate a double bond. It is stuck in this orientation. And so if I have a molecule with a double bond where 2 groups are on the same side of that double bond, they have a cis relationship. And this isomer is different than this isomer, where the 2 groups that are the same are stuck on opposite sides of the double bond because the double bond does not freely rotate like a single bond does. That makes these things 2 different molecules known as cis-trans isomers. This one is cis 1,2-dichloroethene, and this one is trans 1,2-dichloroethene. Rings and double bonds that have at least 2 different substituents can be cis or trans. These types of isomers are called stereoisomers, and they're different than the isomers that we talked about previously. Previously, we talked about structural isomers. These are sometimes called constitutional isomers as well. And structural isomers are things that have the same molecular formula but different connectivity. Notice that the cis-trans isomers on this page have the same connectivity, and the only difference between them is the orientation of their groups in space. What I mean by same connectivity is that the methyl group here and here are attached on the same positions in the ring as they are over here in the trans isomer. The only difference is the direction that they're pointing, but their atoms are all connected in the same way that the atoms are connected on the other isomer. And you could say the same thing about the cis and trans isomers of 1,2-dichloroethene. Please pause the video here and try to answer number 1 through 5 on your activity. Then check the key to make sure that you're correct. We'll go over number 4 together. Okay, let's talk about the isomers that are on question number 4 of your activity. This question is asking you to compare the molecules on the same lines and determine whether they are cis and trans isomers or if they're something else. The first one, hopefully you can see that the atoms are connected in the same way. There are 4 carbons in a row, and there's a double bond between the second and third carbon. If we named these molecules, we would name them 2-butene or but-2-ene. The 2 tells you where the double bond is, and the E ending tells you that it's an alkene. In this isomer, the bond is oriented so that the methyl groups are trans to each other. There are also hydrogens that are on this molecule, but they are not written because this is a skeletal structure. This is a cis isomer. The double bond is still between the second and third carbon and begins on the second carbon. The methyl groups are oriented in the cis orientation, and the hydrogens are also cis to each other, but not shown because it's a skeletal structure. In the second example, notice that the double bond is between the second and third carbons in the first molecule and between the first and second carbons in the second molecule. These molecules are connected differently, so these are not cis-trans isomers. They would have different names because the double bond starts in a different place on each molecule. The first molecule is trans-2-butene, and the second molecule is 1-butene. These are not cis-trans isomers, they are constitutional or structural isomers because they are connected differently. This is also the case for the third example. In fact, these are the same two molecules, except that 1-butene is drawn in a different orientation. Okay, now let's look at the rings. Notice how in the first set of rings, the chlorines are attached at the same positions. They are both on adjacent carbons or in the 1-2 position. So both of these molecules could be named with the root name of 1,2-dichlorocyclohexane. In the first example, the chlorines are on the same side of the molecule, and so this is a cis relationship. And in the second molecule, both of the chlorines are again on the same side of the molecule. In fact, these two things are exactly the same. They are both cis 1,2-dichlorocyclohexane, and they are identical. These are not isomers at all. They are the same thing. If you would rotate the first molecule so that instead of the chlorines pointing away from you, they would be pointed towards you, it would be the same exact molecule. So these two things are identical. In the second example of rings, once again, we have the chlorines attached at the same positions on the ring, but this time, in one example, the relationship between the chlorines is cis, and in the other example, the relationship between the chlorines is trans. So one of these is cis 1,2-dichlorocyclohexane, and the other is trans 1,2-dichlorocyclohexane. These are cis-trans isomers. Notice that their names are identical except for the cis-trans part. In the third example, please notice that the chlorines are not attached in the same positions in the first isomer compared to the second. If the atoms are not attached in the same way, they are structural isomers, not stereoisomers. The first molecule is cis and the second molecule is trans, but they are not cis-trans isomers because their atoms are connected differently. You can tell because the rest of the name is different. So the first one is 1,3-dichloro and the second one is 1,2-dichloro. These are not cis-trans isomers, they are not stereoisomers, they are structural or constitutional isomers. Now I'd like to talk about a different kind of stereoisomer. It is not a cis-trans isomer, it's something called an enantiomer. And this has to do with molecular handedness. Just like your hands have a left and a right version, molecules can be handed. Handed objects are called chiral objects. So when we use the term chiral, it's the same as saying handed. Chiral objects are non-superimposable upon their mirror image. If you look at your right and left hand, notice that they are mirror images of one another. If there was a mirror right here in front of my left hand, the reflection would look just like my right hand. These are mirror image objects, but my hands are not superimposable. I cannot make the back and the front of my hand line up at the same time as I can make my thumbs line up and my pinkies line up. You can't put my left hand right on top of my right hand or vice versa and make them match completely. This means that they are not superimposable. Things that are not superimposable have one important characteristic. There is no symmetry or no line of symmetry in my hand. So there's no way I can divide my hand in two and make one side look like the other. If an object does not have a plane of symmetry, then it will be chiral or handed. Objects that we're familiar with have this handedness or chiral property. Your hands are one example. Your feet and sneakers or gloves are another example. Snail shells also have chirality. And screws might be another familiar example. You know that if you turn a screw to the left, you loosen it, and if you turn it to the right, you tighten it. Righty-tighty, lefty-loosey is the common term to describe this. But if you had a mirror image of a screw, it would not be superimposable upon itself, and you would actually have to turn it right to loosen it and left to tighten it. These are all objects that are handed or chiral, because each of these objects does not have a plane of symmetry in itself. On the other hand, things that are superimposable or have planes of symmetry within them are said to be non-chiral or achiral. They're not handed. Use this nail as an example. Notice that there is a plane of symmetry in the nail. You could divide the nail in half, and one half of it would look exactly like the other. Therefore, when you have a mirror image of that nail, the mirror image would be exactly the same as the nail and would be superimposable. You could take this mirror image and line it up exactly with the original object. So these are superimposable images, and these are achiral objects. Nails, a water glass, even a baseball, a coffee mug, these are all things that have planes of symmetry within them. Any object that has a plane of symmetry within it is achiral, or not handed. Molecules can also be handed. In your activity, it asks you to build a model of this molecule. But let's make it more simple. Instead of making a model with all of these different atoms, let's just make one that has one carbon at the center and has 4 different colored groups on that center carbon. This is a simplification, but it's sufficient to describe the chiral property of this molecule. Please build a molecule like this and another molecule which is its mirror image. When you build them, make sure you set the 2 molecules next to each other and ensure that they actually are mirror images of one another. So if you put one next to the other, it should look like there's a mirror in between the molecules, just like you would if you had your hands in front of you. These molecules are chiral, just like your hands are chiral. And their chiral properties are important for how they interact with biological systems, because many of the molecules in biological systems are also chiral. Chiral molecules interact with other molecules, just like a hand, like your right hand, interacts with a glove. If it is a right-handed glove, your hand feels differently than if it's in a left-handed glove. So a right-handed molecule will interact differently with your body because your body is handed. Most of the molecules in your body, just like a glove, has a certain orientation and a certain chirality. This can be very important in drugs and for the way that our bodies respond to chemicals. Let's take a simple example. I'd like you to click on the link below to see a video about the chiral molecule carvo. Hopefully you can see how chirality is important in biological systems and for the way that our bodies react to chemicals that are also chiral. Any carbon with 4 different groups is chiral. Let's look at another example, because chirality is also important in medicine. Many of the drugs that we take are chiral and have a left and right-handed version. The structure in front of you is the structure for the left and right-handed version of a drug called thalidomide. Thalidomide was one of the most popular and is one of the most successful pharmaceuticals in history. When thalidomide was invented in the 1950s, it was known as the wonder drug that would cure all kinds of disorders, from insomnia, headaches, nausea, to cancers and leprosy. Unfortunately, only one of the isomers of thalidomide was actually helpful in curing these problems, and the other isomer was very toxic to the fetus of a pregnant woman. Unfortunately, thalidomide began being marketed to pregnant women to cure morning sickness. And unfortunately, even one dose of this drug during a woman's first trimester would result in malformation of limbs of her fetus. In fact, there's a whole generation of people in Germany and in Europe and some in Canada that have this problem. Fortunately, this did not happen to a large extent in the United States because Frances Oldham Kelsey was the FDA drug reviewer at the time when thalidomide came across her table to be approved in the United States for a drug for women with morning sickness. Frances refused to approve the drug without further testing and without specifically testing the drug on pregnant mice because she knew that adult mice reacted differently than the fetus of a pregnant mouse. And she was worried that the drug thalidomide could react differently for a fetus than it did with adults. Frances Oldham Kelsey is credited with saving an entire generation of Americans from this horrible tragedy, which unfortunately occurred to the largest extent in Germany. Although the drug companies submitted their application to her 17 times, she refused them 17 times and demanded that they show her proper testing before she would approve their drug. Okay, let's get back to the material. Please pause the video and read the material about chiral objects and chiral centers on your activity very carefully. Then take your model and make sure that you can see how your model matches the wedge and dash structure. It's very important that you can see how this wedge and dash structure matches up with a tetrahedral carbon with 4 different groups attached. If you look at my molecule here, I'm trying to show you that the 2 groups that are horizontal are coming out at you. And the 2 groups that are up and down are going away from you. And they're coming towards me. This model is represented by the wedge and dash structure. 2 groups away, 2 groups towards you are horizontal and 2 groups away are vertical. One way that we will represent this type of structure is with a Fisher projection. In a Fisher projection, it's basically just a shortcut for drawing the wedges and dashes. If I ever ask you to draw a wedge and dash structure, I expect you to represent a tetrahedral carbon using this sort of notation. A Fisher projection is just a shorthand for this. It's just a cross of 2 lines. At the center is the carbon. So it's assumed that there is a carbon here, but in a Fisher projection, you should not draw the carbon. But this carbon here is represented by the intersection of these 2 lines. In a Fisher projection, it's assumed that the groups that are horizontal are coming out away from you, just as they are in the wedge and dash structure. And it's assumed that the groups that are vertical are going away from you, just as they are in the wedge and dash structure shown. It's as if you could smush this 3-dimensional shape onto your page to make the Fisher projection. Anytime you see a Fisher projection, though, know that the 2 groups that are horizontal are coming towards you and the 2 groups that are vertical are going away from you. Spend some time now to make sure you understand this notation. It will be important for you to be able to recognize chiral centers on skeletal structures and other representations of molecules on paper. To do this, we first have to recognize that any carbon with 4 different groups is chiral, and it's called a chiral center. So let's practice recognizing chiral centers. These molecules are on number 5 in your activity. All right, so let's practice. Let me give you a shortcut first though. Any carbon that has 3 hydrogens or has 2 hydrogens is not going to be chiral because it has 2 groups that are the same. So you can ignore any CH3 or CH2 groups. To be chiral, a carbon has to have 4 different groups attached. So you can also ignore any carbons with double bonds like these or this. And you can ignore any atom that isn't a carbon. The only chiral centers that we will be talking about are carbons that have 4 different groups attached. Spend some time now and try to recognize the carbons that have 4 different groups attached. Pause the video here and try to do this. Okay, here are the answers. Here I've marked the chiral centers with asterisks. The carbon here has a bromine, a hydrogen, and 2 carbon groups. The 2 carbon groups here are not the same, however, and so this carbon has 4 different groups attached. In this molecule, a similar carbon has a bromine, a hydrogen, and 2 different carbon groups attached. But in this example, the carbon groups are the same because they're both CH2CH3 groups. And therefore, this molecule has a plane of symmetry, and it is achiral. In this molecule, the only carbon that is chiral is right here. All of the other carbons have at least 2 groups that are the same or have double bonds. Here you have a molecule represented as a sequence of Fisher projections. Each one of these intersections represents a carbon, and each one of those carbons has 4 different groups attached. So they are all chiral. This molecule has only one chiral center with a hydrogen, a primary protonated amine, a carboxylate, and an aromatic group attached. And over here, once again, only one chiral center. We will assume that any molecule with a chiral center is chiral. All right, let's review the types of isomers that we've seen so far. Remember that an isomer is anything with the same molecular formula. So any 2 molecules that are not identical but have the same molecular formula are isomers. In the previous activity, we talked about structural isomers, and these things are isomers that are connected differently. They have different connectivity of their atoms. Things that are connected in the same way can be stereoisomers. Mirror image isomers are called enantiomers. Enantiomer is a word that you will want to get to know. The cis-trans isomers that we talked about earlier are diastereomers, and these are not mirror images. So stereoisomers are isomers that have the same connectivity but a different arrangement of their atoms in space. Enantiomers are the ones that are mirror images of one another, and cis-trans isomers are the ones that are not mirror images of one another. There are also things called configurational diastereomers, but we will not talk about this yet. Please note that the cis-trans isomers are sometimes called geometric isomers, and that your structural isomers are sometimes called constitutional isomers. Okay, this is the end of the video. Please make sure you complete your activity, do your textbook reading, and complete the problems in the chapter. For best practice, complete all of the problems at the end of the chapter as well. Thanks for watching this video on stereoisomers and chiral centers. If you have any questions, feel free to post them in the comments, and don't forget to vote if you like this video.